Good evening, everyone. Welcome back to NPTEL live session, and the course name is Metal Mediated Synthesis 1, which has been taught by Professor Devumitha Maiti from Department of Chemistry, IIT Bombay. And I'll be discussing the three lectures of week 3, and we'll be having next section tomorrow also, followed by problem, whatever the discussion that we regularly have. If you have any doubt, any questions from previous sessions, please let me know either by unmuting yourself or putting a question in the chat box. We will wait for a few more minutes for others to join and then we can start with the session. Thank you. So majorly we are going to take two topics in hand today. So the first topic that is going to be is the coupling reaction, which is Sono-Wishida reaction. And in this one, we will see mechanism, certain examples, and bit more elaboration on the mechanism because here a co-catalyst is also involved. And the second, it's a bit more important, which is Heck reaction. And in this one, we will be talking about the mechanism, examples. We will be taking into consideration the regioselectivity, the stereoselectivity, and asymmetric Heck reaction. So these are basically the topics that will be covered today. So let's get started with the Sono-Kushida reaction. So it's another like Before that, we have already talked about many coupling reactions, for example, Heck reaction, Kumada reaction, Suzuki reaction. So these are another two more coupling reactions that we are going to talk about. So the first one is Sonogashira reaction. So as you know that in various coupling reactions, the names are coming based on what catalyst they are using. Generally, in most of the systems, they are using palladium-based catalyst, but in some systems there is a co-catalyst. There's a replacement of palladium with a 3D metal, like in Nigeshi. We have a coupling partner zinc and it is working with nickel. Uh, then the coupling partners actually play a very important role in these name reactions because, say, for example, if you are talking about Suzuki reaction, the coupling partner is boronic, like organoborane compounds. If you have still reaction that would be involving the tin compounds. Now, if I'm talking about the Sono Kashira, the coupling partner would be different. So here, what we generally have is we have the halide, the RX, and the other reagent is your internal terminal alkyne. And in presence of your palladium zero catalyst, this involves the co-catalyst copper halide. It can be bromide, it can be iodide. Generally, it is copper iodide, which is a co-catalyst. We also need a base here in stoichiometric amount, not a catalytic one. These two are in catalytic amount, and we will end up getting a product which is a now internal alkyne. So we are starting with terminal alkyne. Since this R is getting inserted into this alkyne, sorry, this becomes an internal alkyne. Now here, few factors. First, here R can be either aryl or it can be vinyl. So this reaction is specific for those substrates. The other feature is here the terminal alkyne is the coupling partner. So it is very important to remember which coupling partner, because in most of the reactions you will see the catalyst is same, the starting material like RX, aryl, vinyl, alkyl, they are same. So how it is going to make a difference and how you will remember the name of the reactions, that you need to understand the coupling partners, what we are using and what it is giving at the end. Now, let's quickly take the mechanism into picture. Mechanism of Sonogashira coupling reaction. So, as the starting point, we all know that it will start with the this Ln is the number of ligands. Generally, it is two coordinated with your palladium, and palladium, the active state is palladium zero, because it has to go to first step, which is oxidative addition of that Rx. So this is our substrate. And the first step would be oxidative addition of this Rx. And in that case, palladium will go from 0 to +2 oxidation state, forming palladium R and H. Now it is in +2 state. So once it has reached to +2 state, now the next step would be the transmetallation step, which is very, very important. So what really happens, we have copper X, right? And you have used a base, let's say amine, Nr3, and we have an internal alkyne, terminal alkyne, Hc triple bond Cr dash. Now, when these react, this copper halide makes it highly reactive, and this proton becomes highly acidic that it can be taken away by the amine. And what it really makes is it would form copper alkyne, and it would release, since the H would be taken up by the lone pair of nitrogen, it would form N ammonium and X. So this salt will come out, and this can be regenerated once this copper C triple one C is going to insert over here, and X, this is the step where palladium X and copper alkyne will interact and there will be a transmethylation. So copper X will come out and palladium is going to coordinate it with the C triple one C R dash. So what it would look like? It would look like Ln, palladium still in plus two state. Here it is R, here it is C triple one C triple one R dash. So there, now we have got the two things which are sits in position. Now at the end, it will undergo the third and final step, which is reductive elimination. In reductive elimination, metal again will go from higher oxidation state to the lower one, like losing two electrons. And with that, we will get this R and this alkyne group getting connected, making R C triple bond C R dash. I can highlight this R, which has come from this substrate, right? And this R dash is different. So this is bit straightforward where only three steps are involved. So which are the three particular steps that are involved in this mechanism. First is the oxidative addition of Rx, where R can be aryl or vinyl group. Followed by we have transmetallation step, where if I can write over here, copper X in and this C triple bond C R dash that interacts and makes this particular proton highly acidic in nature, and therefore then Nr3, which is a base, this comes and takes this H, and this becomes minus and then attached onto the copper, making copper C bond, triple bond C R dash, and N is taking H, and the X is coming as like this is a salt. So this particular moiety is very, very important for the transmethylation step. And the last step that we all know that if oxidative addition has happened, reductive elimination would definitely work to retain the palladium back in zero state, going from palladium plus 2 to palladium 0 with R C triple bond C as the product. So, so this is the mechanism of, this is all about this Sonoga-Shira reaction that we have in hand. Let's take few examples for this one. So what would happen if in case like we have dihalide? So in case of dihalides as starting material, whether only one Cl is going to be whether only one Cl is going to be substituted, or it is going to have both the Cl getting substituted or replaced by the reagent. So we have Cl and Cl here. This is dihalide, just effective. So if we have now first step that is going to happen, we are taking N-pentyl and it is coordinated to the carbon C and H. This is an internal alkyne, and this reaction is happening in presence of the palladium catalyst, copper iodide, and the base. And the second step for this reaction is to treat this particular system with another terminal alkyne and giving heat. So firstly, we have to highlight. So there is a possibility of having both alkynes connected to this one. So this is the product that we are going to get. First, we are going to get C triple bond C, and here it is N-pentyl group, and here C triple bond C having silyl trimethyl silyl. So in this case, we can have double substitution happening, double phenyl alkyne groups connected to this particular halide in place of the halide. That can only be possible if we are doing this on auxiliary reaction, because firstly, this is going to react as a full reactive, and after that, once this is done, it is not going to stop, and the other alkyne is going to come into picture to attack on the other side. So this would be our final product for Sono-Kishida reaction. So in conclusion, what we have seen that Sono-Kishida reaction is basically a reaction between aryl or vinyl halides. That halide can be anything, and it is treated with the terminal alkyne in presence of palladium catalyst and a co-catalyst copper. That co-catalyst is required for the transmetallation step. If you see carefully, palladium is firstly in zero state and undergoes oxidative addition of the Rx, giving an Rx coordinated to your palladium, changing the oxidation state from 0 to +2, and followed by when we have a copper X over there and we have a base and we have internal alkyne, they will interact with each other to make a more reactive alkyne over there. And after transmetallation, we will get this step, and in reductive elimination, we get R and R. So, so these were the three steps involved, and we have seen that how halide as a substrate can also undergo these kinds of coupling reactions. Now, quickly, let's look into our second topic, which is the Heck coupling reaction. So in this case, like in earlier cases, we were having alkyne. Now here in Heck case, we have alkenes. So again, we have Rx, and now the coupling partner is your alkene, or you can call it as olefin, in presence of palladium catalyst, and it does not require any co-catalyst in this case, but base is still required in a stoichiometric amount, R, R dash. So here your R is aryl and vinyl. Now let's look into the mechanism in this part. We have palladium 0, and then when we are adding Rx, like first oxidative addition, it would form palladium, R, and X. Now we have alkene, so alkene will first do the coordination. So the first step is your oxidative addition. Second step is the coordination of olefin. When it is coordinating, it will form like something like this way. Now this R group is going to migrate to the beta position of the alkene and making so we will get palladium X, and it would be forming This position it is R dash. Here it is EH already, and one more H is there because this is CH2, and we'll get R over here. And once it is happening, this is called insertion, beta migration or insertion. Followed by that, this is alpha and this is beta. The beta hydride elimination would occur. This would form Ln palladium H and X, and it would again give rise to R and R dash, and ultimately it would release the this HNX in presence of base. They will take BH X minus and R dash. The final product is going to be formed in a transform. So there are many steps involved in this particular reaction. First is the oxidative addition of Rx. Second is the coordination of olefin. Third is the insertion of olefin. Fourth we have is beta hydride elimination. And the final step is reductive elimination to give you the product. So this is what is required in case of Heck reaction. So since I said that in Heck reaction we have a lot of systems and substrates are involved in, so there could be a competition between the reactivities of these systems. So let's see like which are the olefins that would be more reactive towards giving the Heck reaction possibly, and which are not feasible for this. So let's look into first, let's understand first Heck reaction and the relative rates, meaning that we are talking about the olefins reactivity in these conditions. For example, we have normal olefin, which is an ethene, then having a substituent acetate group, or we have a methyl group, or having a phenyl group, so on and so forth. So compared to all of them, the one which is having no substituents would be highly reactive towards this reaction, followed by having an electron withdrawing group. So what it says is, if there is no substitution on the alkene or olefin, the activity is high. Why is it so? We'll see one more time in the mechanism. And this is one such trend. Second trend could be like, if when we are talking about the Heck reaction, we have this, we saw the reactivity of alkenes, like which one would be the better choice to react with. And now we're talking about the Rx. What is the X over there? It's just not the halide. It can be anything. And what would be the rate of the Heck reaction if we change the X? So reactivity rates of X in Rx. So in case of, if I'm taking it as aryl X, because R can be aryl, R can be vinyl. So in case of X, if X equals to N2 positive, it is iodide, it is triplet, it is bromide, or it is fluoride. So the better results are going to come with N2 positive, then iodide, then triplet, then bromine, and then fluoride. So if I am having aryl with this diazo system, that would be highly reactive compared to my iodide. So in this way, the reactivity and the product selectivity you can comment easily. Now, as I said, the different reactivities of the olefin, let's look into the radioselectivity in case of heck reaction, where if we have phenyl group and here it is having bromide or either or anything, and now I'm treating it with alkene, it is going to give me an alkene which is having going to have more substituents compared to the first one. They compare to this internal one, the terminal one, the internal one that we are going to get, it would be having more substituents. So the new alkene would be formed. We can name it as dash, alkene dash, new olefin, right? Now let's look into the reduced selectivity. If we have, so if we have this substrate CO2Me, so there is a possibility of having 100% selectivity at this particular region and no substrate is going to come at this position, right? Now the second one that we have is TN. Again, here it is 100% exclusive product. Similarly, with phenyl group, here it is 100%. Fourth one, with methyl, phenyl, it is meant to give this 100% because that is highly hindered. Now I have this system where it is having H and H over here and one substitution there. So major product would be having 80% over here and 20% possibility of having the substituent at this position. Similarly, if I have where my electron withdrawing group is bit far, and so there are two centers, here it can be 99% and here it can be 1% because it's very close to electron withdrawing group. So the take home message for this radioselectivity part is, so the important points that we have is first, less substituted olefin is having more reactive rates, more electrophilic center gets the substitution in higher rate. That means that would be the position where the phenyl or any group can come and attack. And the C center will get substituted, which is far from the electron withdrawing group. Now let's look into some more examples. So Here, if I have OMe and OMe, so because of the substitute, too much acidic hindrance, it would prefer to have 100% in one only product over there. The other one, if I'm having methyl and here phenyl group, so this is less substituted, meaning like methyl is bit, it is not hindered compared to the phenyl group. So 79%, and this would be 21%. The other example that we have is having methyl and phenyl group in cis position. So here it is 93% and it is 7%. And the other one we have is again OMe, and now it is ME. Earlier we were having OMe, which can be having minor side effect. So now here it is 90%, and now the reactivity has bit increased to go to 10%. Moving ahead to look into the regioselectivity, why we are saying that these kind of substituted olefins make a lot of difference. So we'll try to understand. So say for example, we have taken a system which is phenyl bromide, and here I am having methyl, and it is undergoing reaction in presence of palladium catalyst, the LSPPH3 and base, right? So it's a Heck reaction. Now, the first thing that intermediate after the oxidative addition, the intermediate that is going to form as you are going to have phenyl group here, bromine group here, PPH3 this side, and it is going to coordinate with your alkene, right? Now, there are two positions where this phenyl group can come and attack. This is first position, this is your second position. Now, if you look at it very carefully, so this region is not having any acidic hindrance because there is no substituent. So it is easy for it to get inserted here and thereby forming a product which is like this way, right? Rather than in the other case, if we are having intermediate like palladium, CpH3, Br, and it is coordinated and having, now this side is acidically hindered. For phenyl group to get inserted here. So therefore, this is minor product and sometimes it doesn't even form, right? So this is why uh, the activity highly depends on the substance of your olefin. What are the substance actually? A number and the kind of substance. We have the electronic factors also involved in this one. So let's look into the electronic factors affecting the product of Heck reaction. So we are having, similarly in this case, the example that we have taken. So for example, we have palladium Br, this intermediate that we have earlier, and we have an olefin which is having CO2 ET, right? So if it is having CO2 ET, it would prefer, since it is electron withdrawing group, it would prefer to have the charge minus over here because it is going to take electron density from this side, and this would become delta positive. This would become delta negative. And with the palladium, this is positive and this is negative. Therefore, the interaction between the centers which are having positive and negative, it is going to be more feasible compared to the minus and minus that would be repulsive in nature. And ultimately, we end up having the product, which is CO2 ET. Okay, so that is the thing we need to understand that why at the other position, like at this position, the phenol has not come and attached to it because that would be statically hindered, as well as the electronic factor is there. Firstly, that part is statically unhindered. There is no substituent. Secondly, the CO2 ET part is there, and electronic, even if the both the products is only, which one would be the major product? The first, which is not having any substituents. Second, the electron withdrawing group is far from that particular center. Now we need to understand what is the product that is going to be formed at every single time. So what we have observed that E product is going to, that means the trans product is going to form in almost all the reactions. For example, we have ARX, where X can be anything. We have seen. Now this R is going to get inserted over here. So it would be coming in the form like E product, not as a Z form. Similarly, if we have methyl, it is substituted, and there is bromide, and we have CO2 Me, Me, and again this has to get connected, so it would be coming as a E form. That is the transform, right? So what is the mechanism behind it? Initially that we have seen, if we have Rx plus, say for example, this alkene, and we are treating it with palladium 0 in presence of base. So firstly, what it would form? It would form L here, AR here, X here, and insertion of and coordination of your alkene, right? So this would be the first step. Now, if we look it carefully, like say the addition that would happen, it would happen in this way. If RL goes to any side, say for example, it is going to any of the sides, like because both are same, like it goes to this side. So we have now palladium, and this alkene comes in this particular form. So we have now R here, both the R's. Earlier also it was in synthesis positions. We are keeping it like that way. And AR comes in plane because firstly it has migrated to it has to be in plane as palladium, and palladium is having X and L, right? And H is out of the plane over here and here as well. Now we know that for making beta hydride elimination, the hydride has to come into the plane, and for reductive elimination, the AR has to come into the geometry where it can form the product as of what we are expecting. So this rotation has to happen. So it undergoes a rotation. This is what we call as in case of the synadation. So what it would do, it would the H would have the same that would come in same plane as that is the palladium, so that it can undergo the beta hydride elimination, and the other things will remain as it is. This AR now comes in plane with your R, and that R undergoes. But now you see that the two R that you have taken earlier they were cis in position. Now they have changed their stereochemistry and they have turned to the trans one, and ultimately we end up getting a product which is this way. So, which means it has changed the R and R position. The two have gone to the opposite side. Now we'll see the stereoselectivity of this heck reaction. So we have the substrate as Br, CO2Me, pH, and CO2M, right? In this case, we know that this is the part that is going to be minus, and this is positive. So this is going to attach with, we are going to get a product like this way, CO2Me. And here it would, so firstly, if CO2 is this side, the phenyl of the same will come in the same side. And because earlier it was trans, it will go to the cis, and the now product will come in transition to this one. So this is E product. And these two moieties which were in cis in position, now they have gone to the transform. This is because of the mechanism that we have seen. And we have certain examples for it. For example, we have the bromide, and we have taken PHCO2Me in presence of palladium zero catalyst, ligand, and base. So here we have the alkene, CO2Me will stay as it is. pH now will, phenyl will come in sixth position, and this position we will get our ethyl group. So this will form our 25 into 1% selectivity, the trans includes ratio. Whereas we have an exception in this particular case. Now, if I have phenyl bromide and I'm taking an alkene, which is this CO2M, right? So right now it is in transition because it is thermodynamically favorable. And here in this case, the rotation is not feasible. So what it would do, CO2Me, it would still prefer to be in this state, and phenyl goes to above state because the thermodynamically it is favorable. So this is the product that we are going to get in 12:1 form. The early one where you have seen that the same product was formed, but the substrate was different and the selectivity was higher. Here, in case if the selectivity is bit decreased, like 12:1, because the substrate that we are using, the coupling partner, it is not going to undergo any rotation because of the steric hindrance, and thermodynamic stability is also one factor which is important. Now we'll see the heterocycles example. So if we have ethyl and bromide, benzyl group, when it is being treated with CO2Me, palladium catalyst, base. So what we are expecting is CO2Me will be here, and methyl goes here, and in this position, this is ethyl. So these two, which were earlier in transform, they then became. So this reaction actually works for heterocycles as well. And the last reaction that we have is asymmetric Heck reaction. So if we have a substrate like and phenyl sulfate in presence of palladium 0, L star, where this is a chiral ligand, which can be like R bina. So in presence of base NR3, what you expect to have would be having your side phenyl group. So it's a 92% potential selective product with 70% yield. So then if it works for asymmetric synthesis as well, it's quite useful. So with this, our lecture for today is over, and the rest of the lectures of the week three, we will be taking up in tomorrow's session with the problems. So, so we'll take up the problems now. If there is any question, I am giving you 5 minutes. You just go and revise your concepts that we have read so far, and then we can have our problem session start. Okay, so now we can start the problem session. So this is the first question where you have to match each of the following named coupling reaction with the correct metal catalyst and the coupling partners. So the first one is the Suzuki, and Suzuki involves which catalyst and which system? This is preferably, it's the interesting for example, the one that we have, I'm just going to give you the example of one and the rest of the things that you have to solve. So I'll give you the answer tomorrow. The Heck reaction that we have considered today, that involves the palladium, that only involves the palladium, no copper at all. And that is the reaction for the alkenes. There is alkene, yeah. The aryl halide and the alkene. So Heck is B related with 1 and the 2. So similarly, you have to find out for Suzuki, Kumada, Negishi, and Sonogashira, and then we will be able to, or you can just think about it. Say, for example, Sonogashira reaction, which we have read today itself, Sonogashira reaction, which is E, that is having palladium and copper. So it is having 4 because copper is our catalyst, and we have the aryl halide combination with the terminal alkyne. So this is done. Now looking at Suzuki, Suzuki involves the palladium, which is 1, and it involves the boronic acid. So it is I, the first one. The C, if you see, the Kumada, Kumada involves the Grignard reagent because this was the first reaction that we talked about. So it actually involves the Grignard reagent, aryl halide, and it involves the palladium. So this is also one and third. And Negeshi is the example where we have used the nickel catalyst, which is true, and the organozinc reagent because it undergoes like the reactions which are not able to like for increasing the functional tolerance, the Grignard reagents were being replaced by the organozinc reagents, and palladium is also being replaced by the nickel. So it is four. So these are the answers for like which what was the homework for you, but I have helped you in solving this one. So it is one and it is third. So just go through this one more time and to understand like actually the main reactions are having different coupling partners as well as the metal catalyst. So this is done. Now the second question is which will be the product for the above reaction. So firstly you need to find out like what reaction it is. So it is having a nickel and it is an organo-Grignard reagent where MgCl is there. So type of you can call it as in the category of Negeshi, it can be called as in the category of Kumada. So now we have here a dihalide system. So the question is whether only one halide is going to be substituted or the other would also be. So in this case, this becomes highly reactive. So the two molecules of this one will come and two MgCl2 will come out. In that case, if we have this side, so at this point, we will be having this part firstly substituting Cl, and the other side also we will be having the same thing. So the option A is correct. The third question is the product. The product for this reaction would be, so if you'll see, it's a BBN, which is a borane compound, a reducing agent, and this is therefore a Suzuki coupling reaction where the boron has been involved as a coupling partner. Palladium is there, base is there, and we have OPH, which is a good living group over here. Now, in this scenario, we know that ketone group is not going to go anywhere. So the other two options are anyway eliminated. Now you need to see that, okay, here, this is the part which is going to come and connect, and this is the only part which is going to come and connect over here. So this option is correct. The other options are not right. So what is the role of copper iodide in Sonogashira reaction? We have already seen that in Sonogashira reaction, copper iodide or any copper X over there, it acts as a co-catalyst, not the main catalyst. So option B is correct, A is not correct. It helps in transmetallation, that is true, and also helps in making the alkyne proton pro more reactive to be taken up by the base. So all the three options B, C, and D are correct, followed by which will be the product for the above reaction. So we have here MEMeBr and CO2Me. Now palladium catalyst is a copper X base. So these reactions are nothing but your sorry, this is not having the X plus having the base because it's a heck reaction. So when we have a heck reaction, we know that substitution is going to happen over here, and we will end up getting a product like Ne and CO2Me. That means it becomes the trans in nature. So this is a product that we have already discussed. Now in this case, this also we have discussed that now in place of methylene, there is still the methyl group is less substituted, less hindered compared to the ethyl one. So it would prefer to have CO2Me and this phenyl ethyl group at bottom and methyl at the above part. So this is a cis form and it's a exception you can say because this is thermodynamically stable. So it would not prefer to undergo any rotation when once it is breaking. So with this one, the session for the assignment problems are also being done. We still will be having another 40 minutes to continue. And I would like to know any questions, any queries from your side. Please let me know.